Okay, so empirical formulas are basically, we're trying to get to what we call, do you guys, lowest common denominator? You guys know what that is?
Yeah.
Okay, so what is that?
It's the smallest number a number could be divided by or into.
Okay.
It's a common number.
Common number to get our lowest number, right?
Yes.
So for instance, if we have C4H10, could this be divided by some number to give me a
Two.
whole number, but
By 2.
by 2? Okay. And so we would end up with
C2H5.
C2H5. Okay, so that would be the empirical formula. Okay, simple, not too hard.
Yeah.
Okay, so if I have C6H12O6, then what would be my empirical formula?
6. Oh. C1H6O1.
Is it H6 or H2?
Oh, 2.
Okay, and O. So we don't put the ones in chemistry, they're understood. Okay.
Mm-hmm.
Sorry, I'm trying to get some food in me. Okay, so what about this guy?
P7N. P2N.
P2N. Okay, simple, right? Not too hard.
Yeah.
Okay, so let's move on. Now that you understand what empirical formulas are. So the way that we would determine empirical formulas is if we're given like a mass percentage or the mass of a compound of each element, we first convert those elements into moles. You guys remember how to convert mass into moles, all right? And then we take the ratio between those two elements, or if there's 3 elements, or how many elements there are. So we want the ratio of them compared to each other. The way that we would do that is by looking at the one that had the smallest numerical value and dividing them all by that numerical value and seeing whether or not we can come up with a whole number. So that doesn't make any sense looking on, words on a screen. So maybe we should do a problem. Is that cool with you?
Mm-hmm.
Yes, please.
Okay. Okay. A sample of pure compound is made up of 1.61 grams of phosphorus and 2.98 grams of fluorine. Find the empirical formula of the compound. Okay. Oops. So, what is our givens?
1.61 grams of phosphorus and 2.98 grams of fluorine.
So, the first thing I want to do is change this into moles, right? Because once we get it to moles, moles are quantity, right? So that allows me to compare the quantity of phosphorus to fluorine. So how would I change this into moles?
Multiply it by 6.022 times. Where is the 23rd power?
So would that give me grams to moles? Because So, because that's quantity, right?
Yes.
So that would be atoms or molecules, or in this case, it'd be atoms, right? So, but we have grams. How would I change it from grams to moles?
Divide it
By,
6.022 times 10 to the 23rd.
okay, so isn't that what she just said?
Yeah.
Oh, I thought she said multiply it. Sorry.
No, so she said divided by that, right?
Yes.
So that's Avogadro's number, right? So that's if I had atoms or molecules, or do I have atoms or molecules?
No.
What do I
You-
have?
Do you add the masses?
The masses. Well,
Or
do
the-
I add the masses? I only have phosphorus, so do I have to add any masses?
No.
No. So what can I use? I have grams here.
Phosphorus.
So what do we know about phosphorus?
Can we look for the molar mass?
Well, say that again, please.
The molar mass?
The molar mass. Who was that?
Me. I mean, roll. Sorry.
Okay, Raul. Me. Okay, like I'm psychic. Okay. Okay, Raul. Good job. We need to know the molar mass. What is the molar mass of phosphorus? Anybody? Where would I find it?
Is it 30.974?
30.974. That's right. Where did you find that at?
Periodic table?
On the periodic table, right? So if I have grams, right, I want to use the molar mass. So the molar mass is, we're going to just round up to 31. Is that cool?
Yeah.
So 31 grams of phosphorus per 1 mole. So we're essentially just dividing by the molar mass, right? So then grams are going to cancel out, and then I'm going to be left with moles, because moles is a form of quantity, right? It's not to the particle level, but it's to the like grouping level, right? Kind of like that dozen. So what do I get? How many sig figs should I have?
3.
That's right, I should have 3 because this guy's like a conversion, so we're not going to use that to determine our sig figs. We're only going to use what's given. So what do you guys get?
0.05. Wait. 19?
Okay. Okay, and then what about fluorine?
Be 19 divided by 19.
Okay.
It's 0.157.
Okay. So which one of these are smaller? 0.0519 or 0.157? Which number is smaller?
Phosphorus.
Phosphorus. So then we're going to divide by the smaller one. Didn't you get 3.0 something?
3.02.
Okay, so it's 3.02. Now, can I have 0.02 of an atom?
No.
No. So in this case, we're going to round to the nearest whole number. So we'd round up to 3. Right? So our chemical formula would be P F3. And we use the subscripts to let me know how many I have. Okay, piece of cake?
Yeah.
Okay, good. So if this number had been, let's say it was 3.2, 2, we'll say 3.8. Then we're going to have to try to find a number to multiply it by, because that's too much of a number for it to be just to do the rounding, right? So if it falls within that range, that 0.2 to 0.8 range, then we're going to have to try to figure out a number that we can multiply by to sit there and get it to a whole number, right? So I'm going to give you this little table to kind of help you remember, and I want you to think about it. So, and I'm going to ask you a question. So if the number ends with 0.2, what can I multiply 0.2 by to give me a whole number?
Ten.
Other than the smallest number that I can multiply it by to give me a whole number.
5.
5. Okay. Now, what about 0.25? What can I multiply 0.25 by? .25, a quarter?
2.
Is that going to give me a whole number, or is that just going to give me 50 cents?
Yeah. Then
4.
4. Okay. What about 0.333? What can I multiply by that? By smallest number I can multiply that by to give me a whole number. What is 0.33333333333? Oh, somebody said it. Hold on. That's right. 3. Multiply this guy by 3. Oops. And then that'll give me 1, right? Okay. If it's 0.5, so what can I multiply 0.5 by to give me a whole number? That's right, 2. .667. So what can I multiply 0.667 by? What is 0.667 in fraction form? Anybody?
Would it be 3?
Yes, you multiply it by 3. That's right. Because 0.667 is 2/3, right? So if I do 2/3 times 3, 3's are going to cancel out, and then I'm just left with 2. Okay, what about 0.75?
Four.
4.
Okay, what about 0.8?
5.
Okay, piece of cake?
Yeah.
Okay, let's test it out. We'll see how good you guys are. Can you guys see that? The pink. The compound had
Yes.
40.0 grams of oxygen and 28.0 grams of nitrogen. What is the empirical formula of the compound?
What was the question again?
What is the empirical formula of the compound? You guys don't see the question on the board
Yeah, I see it.
in pink. So what am I going to do first?
Start with the given.
Start with the given. Okay, so we have 40 grams of oxygen. Okay, what am I going to do with that?
You're gonna divide it by 16. And then on top put 1 mole. It's 2.5.
Okay. So 3 sig figs, right?
Oh yeah.
Okay. And then what's next?
The 2.98 grams of fluorine.
We're talking about down here, the pink.
Oh yeah, huh?
Yeah, we're
28.0.
okay. Nitrogen.
Mm-hmm.
Okay.
Be 14 over 14.
14.
Okay.
Equals to 2.
Okay, the next step.
Get divided by the
Divided by
small.
the smallest.
The smallest is
Nitrogen.
Well,
Okay, what do I do next? Or am I done?
No.
Okay, what would be my next move?
You have to round the top.
We have to round it?
Well, I mean, you don't want the three significant figures. But you know what? Never mind.
I have 1.25 and I have 1.0. Is that, can I just round that to 1? Is it NO? Or do I need to do something else?
You do something else.
Okay, what do I need to do?
You just leave it.
What was that?
You don't need to do anything else.
Are you sure?
Well, you're not gonna round it up to 1.3.
I'm not going to round it up to 1.3, but what can I do? What do I need to do since this is 0.25? That's a
Multiply
quarter
it.
of, multiply it, yes. So what I do to one, I have to do to the other. So what are we going to multiply this guy by?
4.
4, that's right.
4.
So we have to multiply both of these by 4. And so then that's going to give us 5 oxygens. And 4 nitrogens. So then our chemical formula is going to be N4O5, our empirical formula. Do you guys get that?
Yes.
So again, if the number falls between, let's say 0.9 to 0.1 to be safe, then you know that you're probably going to use something along these lines, multiplied by these numbers. Try to figure it out. Okay?
Okay.
Okay. So like this one is 1.25. Oh, 25. So N25 multiplied by 4.
Can we do one more?
We're going to do one more, but it's going to be a little different than this.
Okay.
Okay. And plus you got a lot of homeworks that you have to do that I extended.
Wait, can you go back real quick? Either, thank you.
Okay. Okay. Nicotine is 74.1% carbon, 8.64% hydrogen, and 17.3% nitrogen. What is its empirical formula? Okay. So these are percent masses. So if I assume that I had 100 grams of nicotine, how much of it would be carbon?
74.1 grams.
How much of it would be hydrogen?
8.64 grams.
How much would be nitrogen?
17.3.
Okay. So first thing I want to do,
Convert it to moles.
okay, convert it to moles. And we do that by
Molar mass.
molar mass. Molar mass of carbon,
12.
How many sig figs?
3.
3.
Okay. Molar mass of hydrogen?
1 gram, I think.
Okay. Oops. And nitrogen?
14 grams.
For 1 mole.
$1.24.
Thank you. Okay, what's my next step?
Divided by the smallest.
Divided by the smallest. Okay, who's the smallest?
Nitrogen.
1.24.
Okay. So are these guys close enough to round up? Or do I need to multiply them by something?
No, I'm pretty sure you can round them up.
You can round them up.
Okay. Okay, so then my empirical formula would be C5H7N. Piece of cake? So typically, when you're writing the empirical formula of a covalent compound, then carbon, if it has carbon in it, carbon always goes first for covalent compounds. So you'll have carbon, and then you'll have hydrogen, and then everything else goes in terms of the electronegativity. So whoever has the strongest electronegativity would always be at the end. Okay?
Just got it.
So you said carbon always goes first, then hydrogen?
Yep, carbon, then hydrogen, and then everything else is based upon electronegativity. So
Okay, got it.
Okay. Piece of cake? Okay. So when you're trying to find the molecular formula, you first are going to have to determine the empirical formula of the compound. Then you're going to calculate the molar mass of the empirical formula. And then you're going to be either given the molar mass of the compound, or you have to somehow determine the molar mass of the compound. Then you're going to divide the molar mass of the compound by the molar mass of the empirical formula. And then that's going to give you the unit that you need to multiply by. And then you multiply that unit by the empirical formula. Okay. Did you get all of that?
No.
No. Do you want to do an example so you guys can see it?
Yeah.
Okay.
Uh-huh.
Good. So a compound with the empirical formula 2.5 has a molar mass of 58.2 grams per mole. Find the molecular formula of the compound. I don't know what it said. So a compound with the empirical formula C2H5 has a molar mass of 58.2 grams. Find the molecular formula of the compound. Okay, so what's given to me? What are my givens?
That your molar mass is 58.12 grams per mole.
Okay, that's right. So our molar mass is 58.12 grams per mole. Okay, so that's one. So that's of the compound, right? So that's not of the empirical formula. So what do I need to find? The first thing I need to find. So we got the molar mass of the compound.
Would it be the percentage of each one of them?
Not the percentage, but we want to try to get the molar mass, right, of the empirical formula. So how do I calculate the molar mass of C2H5? But that's a good thought, though.
Well, wouldn't you start off with how much each one is per mole?
Okay, so we got 2 carbons. We got 5 hydrogens. Okay, so then 2 times what?
12 per carbon, right?
Yep. And then for
It's 1 each, 1
so
gram.
5 times 1. Okay, we add it together. We get 29 grams per mole. Okay, so this is the molar mass of the actual molecular formula or the molecular compound. And this is the molar mass of the empirical compound. So we're just going to divide these guys by each other. And then that lets me know what I need to multiply my empirical formula by to get the actual molecule that it really is. So if I divide these guys by each other, what do I get? So we then multiply it by that integer. Piece of cake.
Why do we divide 58.12 by 29?
Because this is the mass of the compound. And remember, what is an empirical formula? What is it? How do we normally calculate it? What would be the empirical formula of this guy?
5.
The empirical formula would be what?
No. Like empirical formula is you divide them by 5 to the common number.
Okay, so we divide them both by 5. So that would be C. 4, right? So this here represents the molecule. This here represents the empirical formula. So by us taking the molar mass of the empirical formula and then having the molar mass of the molecule, then we could sit there and figure out we're going to be multiplying by 5 because that's going to be the ratio difference between these two. It's 5. So that's what we're doing here, kind of backwards. So we're given the molar mass of our compound, and then this is the empirical formula. So then to get back what our compound is, we just multiply it by the energy that we get, which is 2. Do you get that?
Yeah, thank you.
Okay. Okay. Questions, concerns, Cash? Okay, so I have a question for you guys. Now that you've been in chemistry for, we're going on 3 months now, right? So since you've been in chemistry for now 4 months, 4 months. So you guys should be experts at everything, right? You know how to name things.
I wouldn't say complete expert, but yeah.
Okay, okay. So you can tell me a couple of things, right? We'll see what you guys can tell me. So what would be some evidence of a chemical reaction? Based upon what you guys have seen or done in labs or?
Are we talking about like in real life, so like heat or something, or are we talking about
That's
like
right,
formal?
heat.
Oh, okay.
In real life, heat.
Oh yeah, so it would be like a smell, heat, physical
So
change.
when you say a smell, what's causing that smell to smell? I mean, how do you smell it if you're not putting your nose right in the stuff?
Oh, you'd have to like waft it or waft it or whatever.
Okay, so that means that you're producing what in that reaction? If you could waft it.
Gas.
Gas. So you get the formation of gas. So that's another example. So we have heat, gas. What else?
Light.
Light, the emission of light. Yep, that's 3. Okay. Got 2 more.
Some reactions get colder as well.
Yep, so that has to do with heat. So that's either absorbing or releasing heat. Okay. Anything else?
Change of color.
Is changing color one?
Change of color. Yeah, change of color. That's good. Anything else? One more.
The noise, maybe?
No, not noise.
Would
Change
it
of
be if
size?
it can conduct electricity?
Not change of size, not conducting electricity. Well, you're not going to change size unless you're building on toothpaste.
I mean, if it's like elephant toothpaste, maybe.
Well, but that has to do with gas for the elephant.
Okay.
What else? What else? Okay. What about solid formation, a precipitant, where you have 2 liquids come together and then all of a sudden you get a solid that falls out. Okay, so those are your 5. Let me share. Okay, so change of color, formation of a solid product, formation of a gas product, absorption or release of heat energy, emission of light. So those are all evidence of chemical changes. So here we have permanganate, and we add permanganate to basically water, and that causes an ion separation. And as a result of that ion separation, as time goes on, more and more of the ions separate, and it goes from a dark purple color to a clear color. So change in color. Here we're adding sodium chloride and silver nitrate. When we add these two together, the silver chloride is formed and it precipitates, making it look cloudy, and then over time, that cloud will actually drop to the bottom and form a solid. So that's the formation of a solid. Plop, plop, fizz, fizz. If we add Alka-Seltzer to water, it starts to make carbon dioxide, and we get the gas, carbon dioxide released in the gas bubbles. You guys like fireworks?
Yeah.
So fireworks, perfect example. It's aluminum and silver nitrate. No, I'm sorry, not silver nitrate. In this case, this would be sodium nitrate. And it causes heat to be released, and then you get those sparks and light emissions, and different color lights depending on the chemicals that you're working with. And then here we have emission of lights, the glow stick. Okay, transfer of heat. So again, cold pack basically is absorbing the heat from surroundings, so it gets colder. And so how many of you guys run into walls and have to use this every once in a while? Okay. Okay, so we're going to be talking about chemical reactions. So we are officially talking about how do we write a chemical reaction. Okay, so I'm going to read this, and I want you guys to help me build this chemical reaction. Okay, it says sodium reacting with water. With solid sodium, when solid sodium is added to liquid water, a reaction occurs, producing hydrogen gas and sodium hydroxide and heat. Okay, so what are my products?
Water.
Is water my products or my reactant?
Hydrogen gas, sodium hydroxide solution, and heat.
Okay, so my products are going to be sodium hydroxide. What is sodium hydroxide? What is the chemical formula for sodium hydroxide? Come on, you guys just finished nomenclature. You just had an exam on it. You know this like the back of your hand.
Ca2HS. Oh no, Ca2OH.
NaOH.
NaOH.
Oh, Na. Sorry.
NaOH. Okay. Okay, so anytime that you see the term solution, that basically means it's in water. So we're going to put AQ in subscript, parentheses subscript, and that's an AQ, not an AG. Okay, and you also told me we produce hydrogen gas. What does hydrogen gas look like?
H2.
H2. And we're going to put G for gas. And we said heat, right? What about our reactants?
Sodium and
Sodium, water.
Okay, so sodium would look like
Na, and then in parentheses S for solid.
Okay. And water?
H2. And then liquid. Do you have to put liquid?
Yes, we do. But is it H2?
H2O, I said.
H2O, okay. I thought you just said H2. I'm like, yes, we're going to put a liquid there. Okay. Okay, so now these are each of the chemicals that are involved in this reaction, the ones that are being produced and the ones that are reacting. So we need to try to balance out the chemical equation. And we kind of did this in the beginning. So what are the elements that are involved in this process? So for right now, we're just going to ignore the heat. So what elements or what atoms are involved in this chemical equation?
Sodium.
Sodium.
So we have sodium. What else?
Hydrogen. Oxygen.
Okay, anything else? Okay, good, nothing else, okay? So how many sodiums do I have currently on the reactant side?
One.
One. How about the product side?
One.
How many hydrogens do I have on the reactant side?
2.
2.
On the product side?
3.
2.
3. There's 2 here and there's 1 there. Okay, oxygen. How many oxygens do I have on the reactant side?
1.
And on the product side?
1.
Okay, so is it balanced?
No.
Meaning,
No.
are they the same on both sides?
No.
No.
No. So which one's not balanced?
Hydrogen.
Hydrogen. Okay, so is there a number that we can put in front of something, in front of one of these chemicals to sit there and help us get it balanced? That's what we're going to do next. Okay, so how many hydrogens do I have currently? I have 2 over here and I have 3 over here. Okay, is there a way that I could get this balanced on both sides, that hydrogen? Because all the other ones, the sodium's balanced and the oxygen's balanced.
Can't you multiply them? So
Right.
2 by 3 and 3 by 2 to make them 6, both?
So when we multiply it, that means we're putting a coefficient in front of it. You don't want to change the chemical compound. So you never, ever want to change your chemical compound once you have it established.
Okay.
So what we can do, you said multiply it by 2. So if we put a 2 here, right, that's going to give you a total of how many hydrogens altogether on that product side?
Oh, 5.
I have 2 here, and then I have 2 times
Oh,
1. So that's a total of what?
wait, I'm kind of lost.
So you see the 2 in front of the sodium hydroxide.
Yeah.
Okay, so that means I'm multiplying 2 by this whole compound. Okay, so how many sodiums do I have now?
2.
2. So I now have 2 sodiums.
Oh,
How many oxygens do I have now?
2.
I have 2 oxygens. And then how many hydrogens do I have?
2.
So I have 2 plus the 2 that I have over here.
Oh, yeah. So 4.
Okay, so that's a total of 4. Okay, so if I come over to my reactant side, is there a way that I can balance out that 2 that I have for that sodium? So there's a sodium here, just one
Yeah, we
sodium.
can put a coefficient of 2 in front of the Na.
Okay, so then that gives me 2 sodiums. Okay, so is there a way that I can balance out those hydrogens?
Yeah, multiply H2O by 2.
Okay, so I put a 2 coefficient in front of it. So then that gives me 4 hydrogens, and that gives me 2 oxygens. So is it balanced now?
Yeah, it looks like it.
Yep, I have 2 oxygens, 2 oxygens, 4 hydrogens, 4 hydrogens, 2 sodiums, 2 sodiums. So that's a balanced equation. You see how that was done?
Yeah.
Yeah.
Okay, so again, rules to remember. The very first thing that you want to do is write down the chemical equation. If your chemical equation is wrong, right, or the chemical formula, if your chemical formulas are wrong, then your whole equation, your whole chemical equation is going to be wrong, okay? This arrow means yield. You don't want to use an equal sign. Never use an equal sign. okay? You're going to either use the arrow going in one direction, sometimes you'll see it going in the other direction, and then sometimes you'll see an arrow going in both directions, meaning like this. Okay? Arrow going in both directions means equilibrium. That means that both you have in that solution that you have both your reactants and your products, and they both are existing at the same time. Okay, so that's what that arrow means. Okay, are we good so far?
Yes.
Okay, so let's see what we can do here. So this is just basically taking you through the process of balancing or introducing you to a chemical equation. The numbers in front are always called the coefficient. So these numbers are called your coefficients, right? And so you're going to be changing your coefficients to balance the equation. So again, the very first thing that we always want to do is make sure that our chemical formulas are right. These are the symbols that we use. You guys are already familiar with them because we had already talked about them. So we have S for solid, L for liquid, G for gas, AQ for aqueous. So anything that's dissolved in water is going to be aqueous. So do's and don'ts, okay? So the do's that you always want to do, you want to make sure that you have the correct chemical formula. So you have to make sure that each of your chemical formulas are correct before you do anything with your coefficients. Then you want to make sure everything is balanced. So you want to use coefficients to balance both sides of the reactions. Okay? Don't. So you don't ever want to sit there and make up chemicals to try to balance out equations, or just change the chemical formula to balance out the equation. So you never ever change the chemical formula to try to balance the equations. Okay? And you never ever make up real or fake chemical species to balance out the equation. Okay, so we talked about the arrow. So your reactants are always going to be on your left-hand side of the arrow, and then your products are going to be on the right-hand side of the arrow. Okay, and you always use the coefficients to balance the equations. You never, ever change the chemical species. Okay, are you good?
Yes.
Okay, so
Yes.
this was the reaction that we had just done. This takes you through each of those steps. So here is another equation. Balance the equation for the reaction of solid phosphorus pentachloride and, solid phosphorus pentachloride and liquid water, yielding the aqueous solution of phosphoric acid and hydrochloric acid. Okay, what are my reactants?
Phosphorus pentachloride.
Okay, and what is the chemical formula for phosphorus pentachloride?
PCl3.
CL.
3.
Penta?
5.
5, sorry.
Okay, is it a solid, liquid, or gas?
Solid.
And water?
Yes.
Chemical formula for water?
H2O.
Solid, liquid, or gas?
Liquid.
Okay, and what are we making?
Phosphoric acid and hydrochloric acid.
Okay, and then what are the chemical formulas for phosphoric acid?
PO4. Oh, wait,
Is it PO4?
H3PO4.
H3PO4. Okay, and then what's going to be the subscript? Solid, liquid, gas, or aqueous?
Aqueous.
Okay. Okay, and you said hydrochloric acid. So what is the chemical formula for hydrochloric acid?
Is it HCl?
It's HCl. That is correct. Okay. Is it balanced? And what are my atoms? What atoms am I going to keep track of?
Fluorine,
Phosphorus.
hydrogen, oxygen.
Okay. On my reactant side, how many chlorines do I have?
5.
On my product side,
1.
how many phosphorus do I have on my reactant side?
1.
1.
On the product side,
1.
1.
how many oxygens do I have on the reactant side?
1.
1.
On the product side,
4.
how many hydrogens do I have on the reactant side?
2.
2.
On the product side,
4.
okay, is it balanced?
No.
Nope.
How do I balance it?
Multiplying by a number.
Multiplying by a number. Okay, what number am I going to be multiplying by?
2.
Let's start with the chlorine. So where do I need to put it? And what number do I need to put?
5 in front of HCl.
Okay. So I have 5 in front of HCl. So now how many chlorines do I have?
5.
5. And how many hydrogens do I have now?
5.
5 plus 3.
8.
Okay. So is that balanced? So chlorines are balanced, the phosphorus are balanced. What about these oxygens? Are they balanced?
No.
Okay, so what do I need to do to balance my oxygens? So I have 1 on the reactant side and 4 on the product side.
Multiply H2O by 4.
Okay. Okay, so then that gives me how many oxygens?
4.
How many hydrogens?
8.
Are we balanced now?
Yep.
Piece of cake?
Are they always gonna be able to be balanced, or will there
Yes.
be like? Oh, okay.
Yes. They will always be able to be balanced. Okay? If the reaction actually exists. Sometimes it'll take you a little bit longer, but you know, it works. Okay. Okay, so to interpret our chemical equation, right? So when we're looking at the particulate level, That means like per atom, right? So we are, or per molecule. So here we have 2 molecules of hydrogen gas is reacting with 1 molecule of oxygen gas to yield 2 molecules of water vapor, okay? So if we're talking about the molecular level, we can have half coefficients because we know a mole is a whole bunch, right? It's 6.022 times 10 to the 23rd. So we could have fractions, or we could have 0.25 of it, right? But in that context here, we could say that 1 mole of hydrogen gas is going to equal a half a mole of oxygen gas. I mean, 1 mole of hydrogen gas plus a half a mole of oxygen gas is going to yield 1 mole of water. Okay, and so that's more at the molar level, the higher level, right? When we scale up. So that's just being, this is saying exactly what we just talked about. So at the particulate level, right? Or when we talk about single molecules at that level, so then 2 molecules of hydrogen gas plus 1 molecule of oxygen gas is going to yield 2 molecules of water gas. When we're talking about the molar level, or in this case, the dozen level, right? So 2 dozen of hydrogen gas plus 1 dozen of oxygen gas is going to yield 2 dozen of water. Okay. Questions, concerns, cash, credit. Okay, good. Okay, so now it always helps if we can classify the type of reaction, because that makes it a little bit easier to kind of predict what we're going to get. Okay, so that means that you guys have to understand the different types of reactions that we have. Okay, and we're going to talk about only about 4 of them, 4 of the major ones, and then some of the other ones just kind of fall in place with those 4. Okay, or just special cases of those 4. Okay, so if you classify the reactions, then you want to sit there and predict. You use your reactants to predict what your products are going to be. And then you want to do a balanced equations, not changing what you have initially. Okay. So first off, let's talk about classifications. So combination reaction is also known as a synthesis reaction. That's basically when you bring 2 or more substances to form 1 single product. So AX yields AX. Simple. Okay, an example. Write the equation for the combination of silver. Write the equation for the combination of solid aluminum and gaseous oxygen to form solid aluminum oxide. Okay, so what are the reactants? Hector, what are the reactants?
Aluminum and gaseous oxygen.
Okay, so what does aluminum look like?
Al.
Okay, is it solid, liquid, or gas?
Solid.
Okay, gaseous oxide, what does that look? Gaseous oxygen, what does that look like? Or what is the chemical compound? Chemical formula for that?
O.
Is it just O?
O2.
What was that?
O2.
O2? That is correct, because oxygen is a diatomic. Okay, solid, liquid, or gas?
Gas.
Yes.
Okay, and that's going to yield, what are we making?
Aluminum oxide.
Okay, so what is the chemical formula for aluminum oxide?
Al O2.
So how am I going to balance this out? Aluminum has what charge?
Oh yeah. +3.
Al2.
It has a, you said I need 2 of them?
Yeah.
3.
And then,
And then 3 oxygen.
okay, yes. Because aluminum has a +3 charge, oxygen has a -2 charge. And then when you put them together, you need 2 of these guys to sit there and balance out the 3 of the oxygens. Okay, is that solid, liquid, or gas?
Solid.
Okay, is it balanced?
Yeah.
Is the chemical equation balanced?
No, we're missing an oxygen and an aluminum.
Okay, so product reactants, we have 2 oxygens, and we have 3 oxygens on the, sorry, 3 oxygens on the product side, 2 oxygens on the reactant side, and we have 1 aluminum on the on the reactant side and 2 aluminum on the product side. So how am I going to balance these guys out?
We're gonna put a 2 in front of the Al.
Okay. Okay, so that makes this guy balanced. Okay, what about the oxygen? Is it balanced?
No.
Okay, so what do I need to do to balance it?
6 oxygen.
6 oxygen. I need 6 oxygen total, or are you telling me I should put a 6 here? Or should I put a 3 here? What was that?
Put a 3 so you can make a 6.
Okay, so that gives me 6 over here. So then what do I need to put in front of here to make it so that it's 6 over here too?
2.
Okay, so then that gives me 6. So that gives me 4 aluminum. So then what do I need to do to fix this?
Change it to a 4.
Okay. Piece of cake?
Yes.
Okay. Good. Oops, get carried away. Okay, so the next reaction is called a decomposition reaction or a dissociation reaction. So that's basically when you dissociate two components. You're breaking them down to 2 different species, 2 or more species. Okay, so AX is being broken down to just A plus X. So when you write the plus, you guys know that means that both of those compounds are in there. It means that they are in the same solution together, but they're not reacting with each other. They're independent. Okay. So water decomposes into its elements when electrical energy is added. Write the equation. Okay. So what is my reactant?
H2O.
And my products? What are the elements? Oh, go ahead.
pH2.
H and O.
H2, solid, liquid, or gas?
Gas.
That's right.
Yes.
And
Oxygen.
oxygen, what? Oh, what?
2.
Okay. Solid, liquid, or gas? Okay, questions, concerns, Cash, is it balanced?
No.
Okay, what do I need to do what do I need to do to balance it?
H2O by 2, and then multiply the hydrogen by 2 as well.
You said divided by 2?
No, multiply.
Multiply it by 2. So you said 2 here?
Yes.
Okay. And the water?
Yes.
Okay. So that's 4 H's, 4 H's, and 2 O's. And 2 O's. Okay. Questions, concerns, Cash, credit.
I got a question.
Yep.
I'm just a little confused on why you put a 2 when you're making the formula where it says where first it was H2 plus O and then you put the 2.
Mm-hmm. Because when we have the elements or we have gaseous or the oxygen gas, when we're just talking about the element, we know from the very first day of class, there are 7 diatomic elements. So that means that when they're in their natural state, when they're by themselves, they're always going to be 2 of them, right?
Okay.
What are the 7 diatomic elements?
Have no fear of ice cold beer.
Have no fear of ice cold beer. That means hydrogen, oxygen, fluorine, chlorine, bromine, iodine, and nitrogen.
Okay.
Okay.
Okay, got it.
A good question. Any other questions? Good. Okay. Whoops. I got carried away. Okay, so certain reactions are reversible or they form equilibrium, right? So this reaction is a reversible reaction. It can go both ways, and so we will have both arrows. Okay. So a single replacement reaction. A single replacement reaction is when you replace one component for another component in a reaction. Often these are metals or they're non-metals being replaced by metals or other non-metals. So a metal replacing a metal or a non-metal replacing a non-metal. Okay. So here you have A plus B X, and then now we have AX B. So that's a single replacement reaction or single displacement reaction. Okay. And often these are going to be redox reactions or oxidation reduction reactions. I like to call it, you're replacing it for a cuter girl, the old girlfriend for the new girlfriend. Okay. So in the case of the single replacement reaction, like I said, it's basically when you're replacing one metal for another metal, or you could be replacing it for hydrogen. Okay, or you're replacing non-metals for another non-metal. So you're never going to replace a metal for a non-metal. Do you know what I'm saying? Okay, so here we have copper reacts with a solution of silver nitrate. Write the chemical, write an equation for the reaction. So copper reacts with the solution of silver nitrate. Okay, so what are my reactants?
Is it copper?
Copper. So what is the chemical formula for copper?
Cu.
Okay. Solid, liquid, or gas? Most metals are
Solid.
Solid.
okay. And a solution of silver nitrate?
Ag. Nitrate, where nitrate? NO.
NO3.
Okay. Good job. Okay, solid, liquid, gas, or aqueous?
Solid.
Nope,
Is it liquid?
Aqueous.
it's aqueous. Anytime you see solution, you always assume aqueous.
Oh, okay.
Okay, so what are going to be my products? Who's going to be exchanging for each other? Who's the new girlfriend? Who's the old girlfriend?
Copper,
Be
the new
copper with nitrate.
Silver.
No, because nitrate is not a metal, is it?
no.
Silver.
Copper and silver.
Copper and silver. Okay, so then we're going to end up with silver metal. So Ag, what should be the substrate?
Don't know.
It's a metal. Is it solid, liquid, or gas?
Solid.
S.
Solid. Okay, and then we'll have copper. So copper, if it's not given, if it's not told to you, you're going to assume that you're going to be making copper too. Because most reactions, when there's a single replacement reaction, most of them will go to the transitional metals. They'll go to the +2. There are a few of them that'll be different, but the majority of them will be +2. Okay, so it'll be copper 2.
+2.
So it's going to be +2, but how many nitrates am I going to need to balance it out?
3.
What is the charge on nitrate?
3. I don't know.
No, it's just negative.
It's a negative, right? So then how many nitrates will I need to balance out a 2+? So really, we're going to have Cu 2+. How many nitrates am I going to need to balance that?
2.
I'm going to need 2. So it'll be NO3, 2. And then we put aqueous. Okay, piece of cake.
Kinda.
I think we
Is
can
it
do it.
balanced? Is it balanced?
No.
Okay, so let's balance it. So under this circumstance, I'm going to show you a couple of tricks, right? Since these guys are going to be replacing each other, and this guy is going to stay together, we can actually just leave our nitrate all together because it's moving as a single unit. You see nitrate over here, and you see nitrates over here. Do you guys see that?
Yeah.
Okay.
Yeah.
So since it's moving together and it's staying together, then we can sit there and leave it together. Okay. So how many nitrates do I have on my reactant side?
1.
How many do I have on my product side?
1.
How many? 2.
2.
2.
Okay. How many silver do I have on my reactant side?
1.
How many silver do I have on my product side?
1.
Copper. How many copper do I have on my reactant side?
1.
On my product side?
1.
Okay. So my nitrates are in balance. So what do I need to do to balance out my nitrates?
You multiply it by 2, the reaction.
Which one? Which reactant? Am I gonna multiply by 2?
Wait, the in front of Ag?
Okay. Good job. So then that means we got 2 here, and that's 2 silver. Okay. So now what do I need to do to my product to make sure that it's balanced? Because right now I got 2 nitrates on both sides, and then I have 2 silver on my reactant side and 1 silver on my product.
You put a 2 in front of the Ag on the product side?
Okay. So are we balanced?
Yes.
Yeah.
That's correct. That's it. Piece of cake?
Kind of, yeah.
Okay. Okay. So I think it's time for us to stop. So I think we're going to stop here.